Hello guys, welcome to my channel. Today I am going to talk about the four basic principles of organic chemistry, that is the resonance, hyperconjugation, mesomerism and inductive effect that we usually seen about it. That for example, that lot of the students, as I have got some more inquiries about it, that they actually get a very confused regarding what do we mean about an electron withdrawing group and an electron donating group. For example, let's say we have this phenol with us. So phenol, we know that these two lone pairs, they will get into resonance like this way, and this one will get minus. So we will get the resonating structure like this. Here will be two electrons and here will be OH plus. After that, these two electrons will get into the conjugation with this bond and this one will be minus. We'll be having the structure like this way. Here will be the minus double bonded OH plus. And in the next step, we have these two electrons will form a bond like this way, and this one will get minus. So we will have the structure like this. This one, and this one will be minus, and here it will be OH plus. And in the last step, we will see that this one will form a double bond over here, and the OH will take up the electron towards itself, as oxygen is much more electronegative than carbon, and we will find the final product to be like this. Now, during the overall case, what we have seen, just let me use some different color such that it will be very easy for you to understand that in this overall case, we have seen that, just a second, that at this ortho position there is minus charge, at this para position there is minus charge, and this again in the ortho position there is a minus charge. So automatically we can think about this, that this meta position will be a delta positive character. Now if I want to just simplify this overall statement, then I will draw the structure like this way, such that it will be very easier for you just to understand that, for example, we have this sort of moiety. Here is the benzene ring and here is OH. So now here this just a second. So here at this ortho position there will be the negative charge associated, as I am showing, and this parameter, that here it will be delta negative, here it will be delta positive, here it will be again delta negative, and here it will be delta positive, and here again it will be delta negative. So now if I tell you that, for example, we are having some nucleophile which is actually present over here, for example there is some Nu minus, so this minus will automatically attack at this meta position, and if we treat the overall molecule with an electrophile which is an cationic in nature, then automatically this electrophile will be attacked by this negatively charged. Like we can tell about that, for example, this OH, and all of this actually happening because of the OH or the phenolic group which is actually present at the phenol, which is actually directing the nucleophilic attack. For example, this OH, it is directing towards the electrophile. That's why we call about that OH as a orthopara directing in nature, and for the nucleophile it has a meta directing nature. Meta directing nature. Now, so I think this is very much clear about all of you guys, that when a molecule or when a particular group, whichever it is present at the molecule, that how it is directing towards a nucleophile or an electrophile. For example, I am now taking another moiety like benzaldehyde. I think the structure of benzaldehyde is actually known to everyone. This is a benzene ring and there is an aldehyde group which is actually present over here. Now you can see very simple that this carbon is having a delta plus character and this oxygen has a delta negative character, because oxygen is much more electronegative than the carbon. So automatically what we can see that this sort of moiety, they have a very basic resonating structure like this way, that this pi electron moves over here and this one becomes minus. So automatically you can see that the cation, which is actually it is making, that here it is becoming a cation, this one will be double bonded C, this one will be an single bonded O minus, and this one will be an hydrogen. So automatically this ortho will be a cationic in nature. Next resonance will take part. So the para position will be now similarly O minus H, like this way. So again the para position will be cationic in nature, and again if you go through the resonance, then you can see that the ortho position will get now the cationic in nature. I guess the structure is visible to you and you can see the structure very well. And in the last case, this minus charge will fall over here and this one will make a double bond at this point of time, and you will get the final structure like this. Like this. And again you are getting the benzaldehyde. So during the course that you can see that if I just forget about what are these resonating structure, then you can see very well that this ortho position is having a cationic charge, this para position is having a cationic charge, and again the ortho position is having a cationic charge. So automatically that means we can say that this ortho position delta plus, this ortho position is delta plus, and this para position is delta plus. Automatically the other two will be delta minus. Now I am telling all of these stuffs with respect to a very renowned book which is known as the Reinhard-Bruckner Advanced or General Advanced Organic Chemistry book, which is named, the authors are Reinhard and Bruckner. You can very simple go through that book and you can understand that this is what it actually tells about. So automatically that means while we are treating any molecule, for example there are any molecule, for example we are having this benzaldehyde itself, that means here it is an electron withdrawing group EWG, that means it is an electron withdrawing group. So when it's of course the electron withdrawing group, then what is actually happening, that this ortho position and the para position they are getting delta negative, and the meta position it is getting delta positive. So automatically now you can say if we replace the aldehyde group with this OH, or which is an electron donating group, that is the EDG, that is the electron donating group, then you can see that as we have discussed in our earlier slide, that this will be a orthopara directing to be a delta positive and meta directing to be delta negative. This is with respect to the electrophile, and this is of course with respect to the electrophile. So that means what we can say, I'm just briefing it out just a bit. For example, let's say we are having two examples just to conclude this resonating parameter over here, that for example we have this sort of moiety and we have an electrophile. Then this electrophile will get attacked with this meta position and you will get a meta directing product. And if we use a nucleophile in this case, then you will get an orthopara product. I think this one is very clear to you, because because as nucleophile is negative and this orthopara are delta positive in character, so they will attack over here and you can find then they will be this sort of product. And if we change the molecule, for example, we are changing this overall thing with like this sort of moiety, where here is OH, which is an electron donating group, EDG, which is an electron donating group, this OH minus. So automatically you can see, if we place an electrophile which is a cationic in nature, then you can see that this one will get into the resonance and this pi electron will attack to the electrophile. I can get the ortho and para products. And if we give a nucleophile over there, then we can see a meta product present over here. So automatically you can see that how if we replace the moiety with an electron withdrawing group or an electron donating group, the overall system changes and the reaction metabolism and the reaction mechanism, it completely changes to a newer extent. Now in an extension to this resonance, we know that we have to find that what are the stability factors regarding which is actually depending on the resonance. For example, we know that, for example, if it's a resonance case, then we have to first know that the molecule should be planar in nature. So the molecule should be planar. So that means once we are having a molecule which has a carbon-carbon sp2 bond, so that means it should have a sp2 hybrid where the molecule is absolutely planar. If the coplanarity is disturbed for a molecule, then the molecule cannot take part into resonance and automatically it will cannot take part into the contrary portion of the stability. For example, we can see that this is a benzene. So benzene, each and every carbon is of course sp2 hybridized. So that means each and every molecule is planar in nature. So now if we just make this like this molecule, this 2 pi electrons gets delocalized into the second bond and this one gets here and this one gets here. So automatically this one takes parts into resonance and you can see that the resonance is taking part here about. But if we change the molecule, for example, at here into the cyclooxatetraene, for example, like this way, it's not a cyclooctatetraene, it's like this. Now you can see very well that this carbon is sp3, others are sp2. So automatically these are planar in nature and this one is tetrahedral. So automatically this one will cannot take part into resonance. So automatically this one will be less stable. Now just coming into the last part of this resonance regarding the stability factor, we need to keep certain things in point to us. For example, the stability regarding the resonance and the stability of canonical structures. Let's say, so what we can think about it. Initially, first, number one, number of covalent bonds. The canonical structures that we are actually getting about, the more we have the number of canonical structures, or the more amount of covalent bonds, the more will be its stability, and it's very obvious. Second, a neutral molecule is far better stable than a charged molecules. This is our second point. Third part, any charged molecule, if the cations versus anions are placed very close, then it will be stable, or else it will be destabilized. For example, cation and anion, they are placing, or they are been placed very close to each other, then they will have a better stability. If they are far apart, then it will be unstable, of course. And we know that cations versus cations, if we see, if they are nearer, then it will be unstable, as like charges repel each other, that we all know. Now this is our third part. As simple as that will be the same because of our anions as well. At the anions and versus anions, if they are nearer, they will be unstable, and if an anion which is close to as a cation, that will be more stable. So the last point that we are going to discuss about it, that when the molecule is charged, so just let's see, if the charges are placed on the exactly the same atom, for example, negative charge is placed on electronegative atom, then it will be stable, and electropositive atom, or rather the or the positive charge which is present over the electropositive atom, then it will be stable. That means we have gone through the 4 points. First point is the number of covalent bonds. If the number of covalent bonds are the same, that we cannot determine the stability, we need to then focus to the next point, that is whether the molecule is charged or not. For example, if the molecule is charged, then we cannot determine whatever is the changes. We need to then shift towards point number 3, that whether the cation and anions are placed together, close or apart. If they are cation and anions are placed together, then they will be more stable, and if they are placed apart, then they will be unstable. And if in that case as well, that the point number 3, you cannot ascertain that whether the molecule is stable or not, then you have to proceed towards the point number 4, where you can see that the charges, if it is an electropositive charge present on an electropositive atom, then it's stable. The negative charge present on the electronegative atom, it's stable. The vice versa is not stable. For example, let's take one example, and I think this will be the end towards our session. Just to understand this thing, we will be discussing about the molecule of diazomethane, CH2 double bond N, it will be plus, and this one will be minus. This is the molecule of diazomethane. Let's say the stability of it. This is the diazomethane, right? So let's draw the resonating structures of it. It's the one. The next resonating structure, it will be like this. Next, what it can happen? That this one is 2. This one can take the 2 electrons. Like this way, and this can take the 2 electrons from here as well. I am just showing this as a dotted line. Some will be plus. And of course this one will be minus. So I guess the structures are very much, this one will be 3, this one will be 4. Now you can see between 1, 2 and 3 and 4 that these two have a higher number of covalent bonds. So that means this 1 and 2 will be more stable than this 3 and 4 as per our the rule. And if we have the second rule, charged or not, each and every molecule is charged. The rule number 3, cations or anions are together or not, both are placed very close to each other, so we cannot distinguish with the 3. So automatically the last point, there is a fourth point which actually seen over here. Now you can see here that here the nitrogen is positive, here the nitrogen is positive. More electronegative nitrogen is having a negative charge. More electropositive carbon is having a positive negative charge. So that's mean this one will be more stable than this one as compared to 1 and 2. And with respect to 3 and 4, you can see more electronegative minus, more electronegative plus. So this one will be more stable. So automatically we can see that from 1, 2 and 3 and 4, that 1 will be more stable than 2, then 3 and then 4. I think this is clear to you. So that means regarding the stability of the resonating structures, you can save this video, you can save a screenshot over it, such that you can go through the overall points that we have understood from this right now, that resonance is a very important parameter to find out whether a molecule which is stable or not. At this point of time, we can see that yes, each and every point that of course this resonance plays a major role creating the stability of the molecule. I think you enjoyed this video. There are actually a lot of parameters that I will be discussing in our next session, that how to find out acidity and basicity parameter of these resonating structures, hyperconjugation and inductive effect. For that you have to stay tuned for my video. After that we'll proceed, and I think this is very important to you. For more interest, that you can directly mail me to chemistryforfun.swapnendu.deb. I will be sharing that in my description. You can send me directly your doubts. You can say me. You can reach to me. I will be solving the doubts to you in our sessions, such that it will be very helpful for you, and we can proceed for the next sessions. So thank you, and thank you very much. For the next session, we'll be discussing about the hyperconjugation, mesomerism and inductive effect, and after that we'll be proceeding towards the solvation of Himanshu Pandey that I have talked about in my first video. And I think that's the most interesting part, because a lot of the students which I am encountering right now, that everyone, they are actually aspiring to be into the IIT Advanced and the JEE Mains and JEE Advanced or the NEET, whatever it is. So it will be very helpful for all of you guys. So just stay tuned. I'm just trying to build up the concept. I'm just trying to make you understand that what are the key parameters which is actually interesting to know before you solve any problems in organic chemistry. So I think this is very helpful for you, and if you find any sort of queries, any sort of suggestions that will be important for me, you can directly mail me or you can comment me at this channel so that I can get through about it. And of course, see you all of guys in the next video. I will be discussing about be prepared. Of course, I'm sorry for about it, and of course, be prepared for the hyperconjugation, inductive effect, and mesmerism. I will be discussing about it, and I will directly proceed towards the solution of Himanshu Pandey. So keep in mind the features of resonance, planarity, stereogenicity, and of course the reactivity of the molecules, which is very important to, as you have seen in this video, that how a molecule is behaving, whether it is going to be an electron withdrawing group or whether it's going to be an electron donating group, such that it can direct their products towards their ortho or para in case of, or in the meta in case of benzene ring that we have discussed. Like we will proceed with a lot of very important discussions and very important topics in our next session. So I will just request you kindly stay tuned, subscribe my channel. If you have any sort of doubts, you can just tell me. I'll be there to solve it for you. Thank you very much.